This is the AP chemistry video for 21st of March 2022, and away we go. I've got it as close as I can, my mini studio here today. I'll try and turn this box a little so you can see a little bit better, maybe a little more straight on. I want you to see the whiteboard without the boxes falling over. It's tenuous here this morning. Okay, hope somebody's there. If you can say hello, say hello. So I know who's out there. I see 3 or 4 of you already, so that'd be great. If you can use the chat, do so. If not, maybe you can use the WhatsApp chat and let me know you're there. Hey, there's one there. Hello, Shilpa. Thanks for getting up early and joining me. At least probably you got to sleep a little bit later because we're not at school. Okay, let's see if anybody else is there. I'll check also our chat here, WhatsApp, and just see if others can let me know there if they're unable to. Quinn is there. And greetings back to you, Quinn. Oh, yeah, now, okay. Aaron can't comment, but is there. So is Lena, Rhea, Tom, Noah, and Leah. Wow. And Noah B is here also. That's great. Noah D and Noah B. There should be a button before you live stream that enables comments, but I don't know. Since I'm getting comments from 2 of you, I think I'm enabling comments. So I don't think the problem is on my side. I've not done anything different than I always do, and normally students can comment. So check your settings. If not, we can also communicate here. It's a little more cumbersome maybe, but okay, so today has 2 goals. One is to take your questions on chapter 6 and 7. Use a non-school account. Thank you, Quinn. So everybody try that. Try a non-school account and see if you can get in there to comment. So do you have questions on chapter 5 and 6? And then if we get that far, or if you don't have questions on 5 and 6, we'll start working on 7. So yeah, so why don't you either type in or comment in the comment line any ones you'd like to look at in the acid-base stuff, so chapters 5 and 6. Hey, there's no B, so you can comment now. That's great. That's great. I'll see if there's any more WhatsApp comments here. I know you're all struggling to get so you can comment, so anything's in the book you'd like to ask about acid bases, chapter 5 and 6. Sorry I left you so long. I was unsure in Austria because I got virtually no questions from you. So I guess it's either going well or you're working together. I hope it isn't that you've given up. But we have 2 chapters to go in the book, and we're going to do it. Okay? They both are chapters that make a lot of sense, and we have a little background in both of them already, so that's not entirely new material. So, once again, questions from you on chapter 5 or 6, anything that you've marked that you'd like to ask me about. Look through your books and see if there's anything remaining. I'm going to give you another minute or 2 to think about that. Now we're getting some questions. Okay, so boop. So first off, Shilpa, number 4 on page 270. Okay, I'm going to put my phone aside. Grab my book. And then Noah B will get to yours as well. Okay, so page 270. number 4. I hope you can see and that's not too much shine on the screen. Okay, kidney stones. Oh, I love this one. Okay, so kidney stones are crystals of calcium oxalate that form in the kidney. My buddy Hutch had some in Montana. Very unpleasant. Kidney stones are passed out of the body easily. Ha! Not easily. But larger stones may block the ureter, causing severe pain. Yeah, that's what can happen. If the Ca2 plus in blood is 5.3 times 10 negative fifth, what oxalate must be present to form a kidney stone? Okay, so here's the deal. We got to go and find for calcium oxalate, Ca, oh, what is it? C2O4, because I think it's plus 2 minus 2. Yeah, it is. We got to do this, right? We got to have that sucker dissolving, so it's going to be a solubility problem. So I got Ca2 plus, you know how this works, plus C2O4, 2 minus, always the same thing. Right, a solid dissolving into parts. In this case, the kidney stone dissolving. Okay? Then we're going to do, well, we're going to answer the question. Okay. What must be the, okay, what must C2O4 2 so we want this. We want this, okay? And we know that what? S of these, when they dissolve, here I'll change colors just to be exciting. When S of these dissolve, I get S of these and S of these. But I also got some more of one of them. What do I got? I got the calcium in the blood, right? Is 5 times 10 negative third molar. So that's this. So I got to go S plus 5 times 10 to the negative third for the Ca2 plus concentration. In other words, it's a problem called the common ion effect, Shilpa. So here we go. Let's do the KSP. Ready? KSP equals Ca2 plus times C2O4 2 minus. I hope that's not too dim. It's looking dim to me. I'll change to blue to see if the blue's any better. And for the KSP, we got to look it up. So somebody want to type in the KSP? Or I'll look it up as you're looking. We'll see who gets first. Hey, I found it. Okay, so calcium oxalate. Ready? 2.3 times 10 negative 9. So 2.3 times 10 to the negative 9th. I just got that from the book data. Okay. In an AP problem, you'd just be given that. Okay, equals. All right, so it's S plus the stuff in your blood, 5 times 10 to the negative third, times S, which is the amount in the oxalate. Okay. All right, let's check this out. This is 10 to the negative 9th. That's pretty tiny. And I'm going to guess that this is a lot bigger by comparison. So what I'm trying to say is this stuff is not very soluble, this calcium oxalate, all right? So compared to the amount that's soluble, I'm going to guess that the 5 times 10 negative third is much bigger. So what we're going to do is we're going to round this and say, over at the side, we're going to say, ignore the first S. So what that's going to do is we're going to do 2.3 times 10 to the negative 9th equals just 5 times 10 negative third times S. All right? And so S is, we'll divide those. Actually, you know what? Somebody want to do that and let me know what you get. I got a calculator. I'll punch it out too. So 2 times 10 negative 2 times 10 negative ninth divided by 5 times 10 to the negative third, 2.3 times, okay, it's not a nice number. Do we have to figure out what to ignore on the AP? Yes, you do, Noah. And the thing is, I'll give you a rule of thumb, Noah, and everybody else. If you can ignore something to make it easier, often they want you to do that, Noah. Like, look, if I hadn't have done this, I'd have had to do what? A quadratic equation. They're not going to have you do a lot of quadratic equations, Noah, on the AP. So normally look for a way to simplify it by ignoring one part of it. Like here we're ignoring the s because the 5 times 10 negative third is probably a lot bigger. Anyway, yes, you'll have to know how to do that, but it is the way. Okay. The answer key had a different number though. Oh God. Okay. Then skip the answer key because I'm pretty sure we did it the right way. So I'm just going to write that show and we're going to call it good. So 4 times 10 to the negative 13. No, that doesn't look right, Chopa. If I divide negative 9 by negative 3, I should get like negative fifth or something. The power doesn't look right to me. You know what I'm saying? Can everybody repunch that out? So I'd have 2.3. Where's the power on this dang thing? I want an EE button on this. Sorry, I'm looking without my glasses on. 4 times 10, there it is. Times 10 to the negative ninth. Divided by parentheses 5 to the negative third equals. Yeah, I get 4.6 times 10 negative 7. I said no B got 2. Thank you, Noah, for checking that for me. 4.6 times 10 to negative third molar. So what does it got to be? It's got to be this. To answer the question, the oxalate concentration has to be this high or higher. So or greater. All right. I hope that's right. Now let me read the rest of your comments. I'm sorry I've been slacking here. Yeah, you can get the right answer, Noah B, with more work, but don't. I don't want you doing quadratic equations. There won't be more than one on the AP, and most years there's not any. So look for a way, Noah, to get around the quadratics. Yeah, thank you, Quinn. Your comment's good. When the number's small and it's being added to a much larger number by comparison. In other words, the negative third power thing is actually quite a bigger number than the square root of negative 9. It'd be around negative fifth or whatever. Anyway, it's significantly bigger. Hey, Ray can comment now. Okay, and could we go over the activity in 5.4? That's the next question I saw. So Noah B, I'm going to turn to 5.4 and look at the activity. Yeah. So Noah, for 5.4, the activity, I don't think I had you do the whole thing. What I did is I had you just sort of fill out the chart. Noah B on page, everybody, 316, the activity in section 5.4. I'll write that on the whiteboard in a second. Oh, yeah. Noah B, do you have a specific problem? Like, were there any of the ones you just want to do one to see how to do it? Or is there a specific one in that activity you want to ask about? or a specific question. So be a little more specific in your question, Noah B. And while you're thinking and writing, I'll erase this and we'll look at that activity and see what it is that we'd like to consider. So this is everybody page 316. That's our acid base chapter activity. Grapefruit juice. How appropriate for the morning. Let's everybody look at grapefruit juice. So here we go. So for grapefruit juice, that actually sounds kind of good right now. We got a hydronium ion concentration. Remember, that's the same as the H plus of 0.0010 molar. Okie dokie. Well, let's just do it. So let's get the concentration of the bleach. You're a tough fella, Quinn. Wow. Especially in the morning. Okay, so remember, here's the thing, right? If I got H3O plus or H plus, as I like to put it, times OH minus, they multiply to get the magic number that you have to memorize, 1 times 10 to the negative 14th. So we got 1, we just plug it in there, although, to be honest, that's 1 times 10 to the negative third. So mentally, I bet you guys can figure it out. Quinn, jump in here if you wish. 1 times 10 negative third, so the OH minus concentration has to be what? They got to multiply to make 1 times 10 negative 14. That's 1 times 10 negative third, so this would be 1 times 10 to the negative. See if somebody can beat me to it here. Thank you, Quinn. Here we go. So 1 times 10 negative 11th molar. So that's a concentration of OH minus. Thank you. And Lena has already the POH, if you think about it. POH is then 11. And so the pH is 3. So the grapefruit juice is fairly acidic. And I think that's what we write for the last comment, right? Sorry, I forgot my H there. The pH is 3, so it's definitely acidic. Remember, the pH and POH add up to 14. Could we have used the natural log formula? That's for buffers. Maybe. I haven't tried it, but I don't think you'd want to do it. I think it'd be a whole lot more work. So just use this and save yourself some time. They multiply to make 1 times 10 negative 14. Then it's just one quick division, and you got the answer, Noah, for getting either the hydronium or hydroxide concentration, whichever one you don't have. And then you can jump right to the negative log of these puppies to get the pH and POH. Here it's nice because it's 1, so we can do it mentally if the front number's 1. Good. And we had other questions, and I think before it scoots off the page, I'm going to write down Rhea's. Rhea says, could we do problem 3 on page 351? Page 351, problem 3. Okay, Rhea. So let me erase this other stuff and jump to 351. Here we go. Okie dokie. 351, the practice problems. Arrange the following 0.1 molar salt solutions in order of decreasing pH. All right, so 0.10 molar decreasing pH. And everybody, if it's decreasing, oh, question from, could we also do milk of magnesia? I'm sorry, I already turned the page before I saw that, Noah. I'll look back. I don't think it's any different. If it's not any different, I'm probably going to say, no, I don't really want to bother. So, Noah, for milk of magnesia, just do it the same way. Divide 1 times 10 negative 14th by 3.2 times 10 negative 11th, and it gives you the OH minus concentration. And then just get the negative log of each of those to get the pH and the POH. They should add up to 14. So I think you can do milk of magnesia on your own. And question from Shilpa, would a pH, for example, a 6 be considered relatively neutral or still acidic? It's still acidic. We would call it slightly acidic, Shilpa. Mhm. Is that also drinkable? Yes, probably, depending what it is, unless it's something like strychnine or arsenic, in which case, Quinn, even if it's not so acidic, you still wouldn't want to drink it for other reasons. Okay, so increasing POH. Did I read it wrong? Are you correcting me, Noah? As is so often the case. Arrange the following in order of decreasing pH. I don't quite get your comment, Noah D, because it does say decreasing pH for this problem. In other words, we're getting more acidic, aren't we? More acidic. All right, so what we got to find are the Kas. That's what this problem's really about. So we're going to have a um, we're going to have how do I want to say this? Increasing Kas. So increasing Ka values. Or some of them might be basic. We can kind of sort them out. Oh, yeah, I see what you mean. Thank you, Noah D. Yeah, you're right. I tend to think in pH and not in POH so much. So what we got to first do is we got to mentally put all these suckers in water. You know what I'm saying? Okay, let's look at them chemical by chemical. We got 4, right? Let's look at the last one first. Ready? NaOH, NaNO3. What do you know about Na plus and NO3 minus, everybody? They're both what? They're both from what? Hint, it's going to affect the effect of this salt on the pH of water. Both Na plus and NO3 minus are what? Soluble, yes. And they both come from strong acid, the NaOH, NO3, and the strong base, NaOH. So these both will, because one ion comes from a strong base and the other comes from a strong acid. There it is, Rhea, thank you. So there's no effect on the pH. So the pH is about 7, close to what water is normally, all right? Okay, now let's see what the next one does. In other words, we're not going to have to figure out the Kas for all these suckers. Okay, let's look at the next one. FeCl3, not the next one, the first one. So we did this one in lab, right? Remember Fe3 plus, that iron ion? So if we add it to 3 waters, remember water's made of, think of it as like H plus and OH minus. So I'm going to pull off some OH minuses. And I get FeOH3 plus 3H plus, or 3 hydroniums, 3 hydroniums if you want. Either way, it's very acidic. We found that out. In fact, you guys took the pH in lab, if you remember, and it was pretty low. I can't remember what it was. You can probably look it up. Okay, before we worry about any numbers, let's do the last couple and see what else we got. All right, I got ammonium carbonate. All right, so ammonium and carbonate. Okay, so ammonium will break down and give off an H plus I got a NH3. How do I know that? Because it's already plus, you're probably not going to add another H plus onto there. And we can look up the Ka values. Let's see if I can find it quickly in this chapter. No, I can't. So I'll just go to the back of the book. I hope it's there. But I'll just look up both at once. God almighty. Okay, so this one, this is going to do the opposite. Look at that. It's going to make a base because it's going to grab, whoops, I got to do it this way, plus water, forms HCO3 minus plus what's left, OH minus. So here we got one going making H plus and the other making OH minus. We got to see who's stronger, right? Remember how this worked? Okay, so I got to have data. So I'm going to the back of the book. And again, on the AP, you'll have the data. Oh, please be here. Here it is. So it's page 567, okay? Yes, it's a pain, but that's life. You got to look them up. So for NH4 plus, ammonium, it's 5.6 times 10 negative 10. And for, pardon me, for for carbonate, and I got to look on the other side for that now. And I don't know if I have a single carbonate. Maybe I got to do this thing going to H2CH, H2CO3. Hold on. Do I have regular carbonate? So therefore I need HCO3 on the left side and carbonate on the right. I got it. Okay. Hydrogen carbonate ion. So the Ka, I got the opposite. So it's, all right, you ready? If you look on page 567, look at the bottom, the number 5.6 times 10 negative 11. That's the Ka for HCO3 minus breaking down, but it's not breaking down, it's forming. So the Ka to form that sucker, let me think about it. Is essentially going to be the Kb. Oh, I really got to think about this. Hold on. So carbonate is really going to be a Kb here. Yep. And so it's going to be 1 times 10 negative 14th. Remember doing this? The Kw, 1 times 10 negative 14th, divided by the Ka. And the Ka, again, I'm ancient, so I got to look it up, was 5.6 times 10 negative 11. So it's going to give you something around the negative third power, all right? But Mr. Weiss, how come you're not finding it? Because I'm lazy, and because the problem doesn't say I have to find everything exactly. This looks like the hardest frickin' one. Let's look at the last chemical. Okay, so what's my point here? Look at this one. I had ammonia, ammonium, and carbonate. And the more important one is clearly the carbonate. Look at it. Its Kb is much bigger, so that's going to make it kind of basic. All right? Because that's a much bigger number than the Ka for the ammonium, 5.6 times 10 negative 11. You know what I'm saying? So the Kb is bigger than the Ka here, so that's going to rule the day. So this is going to be a basic solution. And how basic? Well, around a Kb of whatever times 10 negative third. Okay? Yeah, maybe I should not be so sloppy. So it's not -3, it's 10 to the -3rd, something or other. Okay, so what we've got to do is, I'm going to mark that page, dog ear it here, is we got to go back and do the last chemical. The last chemical is aluminum. Um, oh God, the last chemical is kind of involved too. So the last chemical is aluminum, and it's the same as up here, but so it's aluminum plus 3 waters. To think about it, we did this in lab, those that were there. Makes aluminum hydroxide, OH3 plus 3H plus. So that's very acidic. We got the pH in class. Let's see what the other one does. CH3COO. Well, this is a base. Yeah. So I'm going to add CH3COO minus to water. Hope you can still see this. And it's essentially going to be a KB. So what that means is it's going to take an H plus off the water. So we're going to get HCH3COO plus OH minus. Okay, hoo-ha. So I need the KB for this sucker, okay? So again, I got to go to the back of the book. For a short problem, this is pretty involved. That's life, okay? And go back and I got to find the ammonium. So what's called acetic acid. So find acetic acid. And there it is. So the Ka is 1.8 times 10 negative fifth. All right, so the Kb is 1 times 10. Okay, so let's get the Kb. So the Kb is 1 times 10 negative 14. And again, I'm getting the Kb because I found it's making base. Therefore, I know it's a Kb. I got to look up. That's how I know that. I know you think I'm just pulling this stuff out of my head. I'm just using the equation to guide my logic. Otherwise, I couldn't do it. Okay, I got to divide that Kw divided by the Ka value. Okay, the Ka, I know what it is. I've had it for years. 1.8 times 10 negative fifth. 1.8 times 10 to the negative fifth, which is about a Kb to the negative ninth. 10 to the negative ninth. And the aluminum, oh golly, this is a tough one because we got aluminum and iron. Those are both probably acidic, and probably more important, this is pretty low. I'm going to guess it's going to be more acidic. So really it's between these two, isn't it? I'm looking to see if she had any sort of shortcut. I think she did not. So we got to figure out a way to separate which one is more acidic, the Al3 plus or the Fe3 plus. So let's see if there's anything back here that can help us. There's iron hydroxide. Iron 3 hydroxide. What I'm looking at here to help me figure out which is more acidic, the one with the iron or the one with aluminum, is I'm looking at the solubility product constants on page 566. And I found iron hydroxide, and I'm looking for aluminum hydroxide. And of course, the damn thing's not on there. How am I supposed to do this then without that data? That's annoying, Cheryl, because normally it's pretty clear what to do with the data. Okay, so we're going to just fudge it. You ready? Because without data, you're not going to expect it to know this. So, Rhea, here's how you're going to answer this question. Let me get to the page again, 351. Okay, what do we got here? I'm going to mark it in red. The one that's basic is going to have, we're going to more acidic ones. So the one that's basic is going to be out here. And that was so the order, the first thing, the one that's going to be the least acidic, the basic one will be NH3 or NH4, probably 2. Do they at least give you the chemical? Yeah, they do. CO3. So that's going to be, so what are we doing? We're doing decreasing. So that's going to be greater than, so the pH of this stuff would be greater than. Then there's the one we had for NaNO3, right? That's pretty close to water. 7. It's not going to have a big effect either way. So that's going to be then our next pH. I'm going to erase some of this crap. And then we got, so that's going to be greater than the pH of NaNO3. And that's going to be greater in turn than the 2 that we've got as acidic, okay? And I can't find the data, so if we can't have data, then we can't separate them. The only way we could separate them is you guys did them in lab, but you're not going to have to pull that idea out of your head for the AP. So I'm just going to say it's going to be a tie for the last 2, and that's going to be, wait a minute. No, it's going to be easier. It's going to be easier. Okay, everybody look at the 2 chemicals for a sec. FeCl3, do either parts of that come from a strong acid or base? The Cl minus comes from HCl, so I don't have to worry about Cl minus. You know what that means? That means that the Fe1, Fe3 plus is going to be more acidic because the base doesn't matter. So that's going to be out here. I didn't have to do all that frickin' math. God almighty. So FeCl3 is the most acidic. So the lowest pH. And again, follow my reasoning. Look at the last chemical that I haven't talked about again, the aluminum acetate, AlCH3COO3. Everybody look at that? Okay, the aluminum makes it more acidic, but the acetate makes it more basic. And we said the acidic's probably going to win, but it is fighting with the effects of the base. So I'm going to guess that that one is going to be less acidic than the one that has the iron, because the iron is attached to Cl minus, which doesn't really affect the pH. You know what I'm saying? So if I got one battling, they're not going to be as acidic as the one with FeCl3. Okay, so I think that's the order. Al and then acetate CH3, COO, and 3 of those puppies. That was a long lot of work, and I didn't need to do a lot of that, Rhea. I should have just used my head. Sorry that took so long. So if you had data, you could actually numerically figure out all of the pHs, but we didn't really have to. We just had to figure out the order. So that should be the order. Okay, other questions about that or other questions from you? And if I didn't answer your question in the chat, I'm sorry. I'm trying to read through and see. Okay, so ask me any others. I'm also going to check my phone and see if anybody put in some questions in the WhatsApp. Okay, hold on. My tiny office, I got to find my phone here. All right, let's see if you got any questions on the WhatsApp. No, I don't see any questions on the WhatsApp. So any other questions here on chapters 5 and 6, acid-base stuff? Yeah, we do. So got one from Lena. So I see 393, number 8. Thank you, Lena. I'm sorry I left you alone for so long, and here I am with Corona, even though I feel fine. Stuck here this week, so I won't be able to see you till next Monday. It really ticks me off, but we're going to do this all week. I'll do videos all week for each class, and even if you can't make them, you can watch them and see what's up, okay? All right, so page 393 and number 8. Good, and I'll change back to blue for solving it. Maybe that's a little easier to see. I don't know. $393, number 8. We got some acid and base that we're doing. Okay, so I got 4.48 liters of HCl gas. Don't put your finger in that. Measured at STP is dissolved in enough water to produce 400 milliliters of solution. A 25 milliliter sample of this is titrated with blah blah SrOH2. What volume of standard is required to reach the equivalence point? Okay, first thing we got to do is smell something. And I don't mean smell the HCl gas because that would hurt your nostrils. Oh, question from Noah. I'm sorry I saw that so late, Noah. Why do we plug in 5 times 10 negative third in the first problem? Ooh, that was a couple problems. That was given. That's why, Noah. It was given for the concentration of calcium in your blood. So we had to put that in for the calcium concentration back in that problem, if memory serves. So that was given. We had to use that data. Okay, all right. Okay, so Lena, we got to smell out the Pivnert here. It's a gas, and we've got to get how many moles of it. And then we can divide by the milliliters to get the concentration. You ready? So smell it out. Here we go. We got PV equals nRT. We're going to solve for N. So PV equals nRT. So RT going to be down here. And PV. So like that. We got to get number of moles of HCl. That's the Skupski. Alrighty, here we go, folks. So let's put that in. I'm going to do it over here to save a little space. The pressure, it's standard pressure, so it's 1 atmosphere. The volume they give us, 4.48 liters. The R value, we're going to use 0.0831 liter atmosphere mole Kelvin. Yes, you'll be given that on the AP. Times the temperature. It's standard temperature, and I think that's 25 degrees. Am I right, people? Are we doing standard should be that. I'm going to do a quick look here because I've been away for this for 3 weeks. And make sure that's what she's doing in this chapter. Anyway, I think it's 25 degrees C. So that'd be 298. Stop me if I'm wrong, please. 298 Kelvin. I don't think it's a 0 if it's standard. At any rate, okay. So somebody want to get that? Somebody got it already? How many moles is that? Can you guys punch it out? You're going to be quicker than I will here because I'm in my teeny tiny little office. And while you're thinking about that, the rest of us can continue. So we're going to get the concentration of HCl, which will be the answer divided by the number of liters. And it's in 400 milliliters, so 0.400 liters. Okay, what you guys get for N? Thank you very much. Oh, look at that. Lena's already there at the N. So it's 0.18. Yeah, it's 0.0831. That's the R value, Aaron. Okay, so Lena, you already got it. And it looks like 0.183. Okay. Now, is that the answer after you divide by 0.4, everybody? Because this wouldn't be molar. Like, is the answer you're giving me this one? Or is it up here? Is it the number of moles? So Shilpa and Lena, is that the number of moles you're giving me? Or the moles per liter once I divide by 0.4 liters? In other words, does it belong up here or down there? The number of moles. Ah, okay, so thank you very much. All right, both of you. Good. So then let's divide that by 0.4 liters. Ready? 0.183 divided by 0.4. And let me know what you get for that. And that'll be our concentration of HCl. Then the rest of it is a whole lot easier. Thank you, Rhea. That looks good and clarifies it too. I love moles. I do too. They're cute. You can almost reach down and pet them. Millimoles are even better. Okay, so somebody get that for me? So 0.183 divided by 0.4. Glad you're in a good mood early in the morning. I am too. The rest of it will be easy, by the way, Lena. Okay, Lena's got it. 0.458. Others can check that with an M for molar. Thank you, Lena. And let's now do the problem. Okay, so here we go. The problem actually says what volume of the standard solution, and I think that's the strontium hydroxide, is required to reach the equivalent point. Okay, so we're going to do this. Ready? Acid, moles of acid equals moles of base. Now, don't tell Sherry I did it this way with you. And Noah says, Tom, and I need to get ready to go to school now. That's okay. You guys go. Just watch the rest of this later because this problem is probably a pretty good one to look at the ending of, okay? All right, bye-bye. Everybody else, you can let me know when you're leaving and I'll just blather on, but at least I won't ask you to crank out any more answers because you won't be there. Okay, so don't tell Sherry I do it this way. She hates it, but I like it. And it goes like this. We're going to do concentration of the acid. So M of the acid times the volume of the acid equals concentration of the base times the volume of the base. Does this look familiar? I hope so. We used it for dilutions and other stuff too. It's going to save you time. Okay, you ready? Don't get lost in the details, but put the details in. Ready? Here we go. The concentration of the acid is this. It's 0.458 molar, what you just got from me, Lena and others. And how much volume is that? It's 400 milliliters. So I don't care if you can put it in milliliters or liters. Let's just put it in liters. So 0.400 liters equals, now here's where the base gets tricky. Ready? Check it out. It's SrOH2. So what do I got to do with that concentration? Hint, hint, hint. SROH2. So I got to take the concentration. Just spit on myself. I hate when that happens. I got to take the concentration and da 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 da. Can you beat me even from far away? Well, I'm going to start writing the number down. So concentration 0.227. Double it. Thank you. Exactly. Ah, the answers are rolling in. That's my people. Times 2. And if you do that, even though Sherry doesn't like it, this formula works just fine. Okay? Times X, or whatever you want. Volume of the base. And I think I may leave you to solve that little part. Okay? Let me read it one more time, Lena, but I think you can finish it up from there. Yeah. Oh, I screwed up though. I screwed up. Who found my mistake? Read the problem again. We got to go back and it says a milliliter sample of this solution. So it's not 400, is it? So it ain't over till it's over, at least not till Mr. White screws up. So they're only using 25 milliliters of that. So you're gonna have to change that to 0.025 liters. Okay? So of the 400 milliliters, they're only titrating 25 milliliters just to make it more complicated, really. But I think now you can really finish it up. Okay? Other questions from all of you? Chapter 5 and 6. Thanks for your hard work. I know that those chapters were long, but they are super important. I think the last 2 chapters you'll find to be A, shorter, B, more like stuff you already knew. All right? So you're through the hardest part of the course, in my opinion. Acid-base stuff is like the guts of AP. It's like the liver or the lungs or something, okay? Maybe the lungs, although it might be hard on your lungs. Anyway, never mind. Okay, any other last questions on chapter 5 and 6? All right, it's cold in my basement, so I'm going to blow my nose. And I don't see questions. And I'll check my phone one last time. Whoa, I almost knocked you over. Don't lose your class. You're sitting on top of 2 cardboard boxes, by the way. So if you feel a little rickety, that's probably why. Okay. That's fine. All right, so here we go. Let's talk then about chapter 7. At least let's get into it, okay? It's some stuff you and I already talked about. So here we go, chapter 7, 7.1. And it's about entropy. So entropy, and I think Quinn probably had this because I think we talked about it. It's more or less about amount of disorder. Amount of disorder. And so what we have is this, delta S, and that's the change in entropy in a reaction. Is it getting more disordered or less? I think we had this, didn't we? So if it's a positive delta S, means the products are more disordered. And if it's a negative delta S, you guessed it, Chester, The reactants are more disordered. You can just quickly put that, all right? Did I catch COVID on the trip? You betcha. Nothing like a little souvenir from my 8th grade buddies. Okay, so what does disorder mean in terms of chemistry? Okay, so I'm going to say more disordered, if I can spell disordered. It was a nice group, by the way. Nice group of 8th graders, but COVID made it so several got sick. So it means either more numbers of moles so more particles, or more moles of gas or liquid. Okay, so if I break this up, here's CaCO3 solid. If I break it up into CaO solid plus CO2 gas, I got what? I got 2 reasons it's more disordered, right? I got 2 particles instead of 1, and one of them's a gas. So this definitely is going to have a delta H, right? So very much a positive delta S. Sorry, not H, S. Okay, because I got gas and I got 2 things coming off instead of 1. So that makes more disorder. Okay, here's a fun thing, but it's more physics than chemistry. The 2 laws of thermodynamics. One we had before, right? The law of conservation of energy. Energy can't be created or destroyed. It can just be changed form. Okay? And that law I consider to be you can't win. Okay? I can't create something from nothing. So that's the you can't win law. The second law is entropy, disorder, is always increasing in the universe. What that means is whatever I do, I often get some entropy, and the entropy or disorder is often in the form of heat, by the way. So if I'm using like trying to make some new source of energy, I can't even break even. There's always going to be some heat forming that's fairly unusable as an energy source for humankind, for example. So sometimes physics say the first law means you can't win, and the second law means you can't even break even. Okay, a little pessimistic, but that's kind of the way the physics works, so to speak of. For chemistry, Sherry gives you an equation to get the amount of disorder. You're not going to have to do that on page 441. Forget it. That's not important. But she gives you a couple things that might be useful. Okay, to get the delta H or delta S, I'm going to erase this now. And again, this video I'll have on the live stream in case you missed some of it. So to get the delta S, the change in entropy or disorder, now she has it as the delta S of the surroundings. We'll have to think about that as we go. It's equal to the Q, or heat, remember that's what heat was, divided by the temperature. But that's also equal to the negative delta H divided by the temperature. So let's remind ourselves what that means. Okay, so Q is like the heat, in this case, of the surroundings. And the delta H would be like if it's exothermic and if delta H is negative, then I'd have a negative against a negative and make it positive. So if my reaction gives off heat, then the surroundings absorb heat. So that's why they're opposite signs, if you catch my meaning. The surroundings will absorb heat, so that'd be positive. Where's the heat coming from? The reaction, so that would be negative. Okie dokie. That's you're going to do a couple calculations with this, but it's not so crucially important. Let's get to the important stuff, all right? And I'm on page 443. Here's an important thing. And it's easy. It goes like this. To get the delta S of a reaction, you can guess what I'm going to do. I'm going to get the S of the products minus the S of the reactants. Well, what a big surprise. We've done that many times, haven't we? We've done that with delta T. To get the temperature, you subtract the temperatures, the pressures, you subtract the pressures, the H, the heats of reactions, you subtract those, products minus reactants. And where are we talking? We're talking data. Where do you get this data? From page 570, okay? So page 570, S, H, and G data. What the heck is H and G? You'll find out. It's not hard. Okay, but the S data is there, or delta S data, okay? So more or less, you just sort of say, hey, look up the data, crank it out, and see what's more and what's less. And that, my friends, I think is it. Okay, now we're up to section 7.2. You might say, well, section 7.1 is pretty short. It is pretty short, and you already got the idea. It's entropy and realizing when it increases, and numerically when I can calculate it, and how if I need to, with either this or less important is this one, but most important is this puppy right here. The delta S is S of products minus S of reactants. Oh, I said reactions. I meant reactants. Sorry. Otherwise, it doesn't make any sense, right? Huge. So section 7.2 is about Gibbs free energy. Gibbs was not one of the Bee Gees. Oh, that's a really old joke. The who, Mr. Weiss? Yeah, never mind. But Gibbs studied to find out if reactions are spontaneous or not. So we're going to look at what that word is. Well, she gives you the equation right away. So let's just see this. Okay, here's the equation, okay? Gibbs free energy is delta G. Oh man, that's a terrible delta. Delta G. And the equation that you're going to memorize and hold dearly in your heart forever and ever is this equation because it's so useful. Delta G equals delta H minus the temperature times delta S. So T delta S. That sucker, believe me, you won't have to memorize it. You're going to use it so much you'll know it. And it's really, really a good equation. Okay, so what is Gibbs free energy? Backing up. What is delta G? Okay, if delta G is negative, reaction, I'll abbreviate that to RXN. Reaction is spontaneous. And of course, if delta G is positive, the reaction is non-spontaneous. Well, what does that mean? They cried in terror. And there's the rub, okay? And this is the part that will make total sense to you in just a minute. So I'm going to let you catch up here. So if the delta G is negative, the reaction is spontaneous. If it's positive, it's non-spontaneous. Okay, so what the heck is spontaneous? And who cares? Well, the universe cares, as it turns out. So spontaneous, just to tell you spontaneously, I'm going to read what Cheryl says, and then I'm going to kind of, oh God, she's using TherFab, thermodynamically favorable. It means basically a reaction occurs on its own, and that's once you add in the activation energy, okay? Like if I light a match to a stick of dynamite, if I light a stick of dynamite, once that sucker starts and blows, I'm not going to stop it. It's spontaneous, it's going on its own, okay? So reaction occurs on its own once the activation energy, act N, is added. The word that the gurus use in AP chemistry is it is thermodynamically favored. Which to me is ridiculously long. Thermodynamically favored. Example, dynamite. Exploding after you light it, after it's lit. And then I'll put a little blue line and say, here's one that's not so. Oh, okay, dynamite exploding after it's lit, so we'd have a negative delta G. Okay, again, negative means it's spontaneous and it happens on its own. Okay, let's do a positive delta G for you. Okay, positive delta G. So here's an example. Plastic not dissolving in water. Yes, I know there's a few plastics that dissolve in water, but for the most part, they don't. This is why we have such a problem in the oceans. Lots and lots and lots of floating around plastic. So it's because the delta G for plastic to dissolve is positive. It's not spontaneous. So we're stuck with all this stuff floating in the ocean, okay? It doesn't break down easily. So that's why the universe matters. No, that's why delta G matters to the universe. Does something happen or not? And it really depends on two things, okay? Depends on, did I erase it? No. It depends on the entropy, the delta S, and that's related to temperature. Generally, higher temperature, more entropy, more disorder. That's why it's T delta S, by the way. Think of it, if I have like sugar on a stove in some water, I can dissolve more sugar at a higher temperature because there's even more entropy because I multiply the temperature times the change in disorder. That is one sort of part of the universe. The other part is delta H. Is heat given off, or does heat have to be absorbed to make something happen? So it's kind of like a battle between these two, okay? So who's going to win? The heat or the entropy? Okay, delta H or delta S. That's what delta G is. It's like the great scales of the universe. So it's very philosophical. Who wins? Entropy, disorder, or energy? We call this minimum energy or maximum disorder. Who wins? They're always opposites to each other. And the winner is delta G gets to say. Okay? Ute. Maybe we should look at some of her examples. Let's see if we got questions. Would the dynamite before being lit also be positive G, since it can't happen on its own before it's lit? I think it's still looked at that way, Shilpa. In other words, when we talk about delta G, we ignore the fact that you've still got to put in some kind of activation energy. So I think that delta G assumes that we're lighting the match, so to speak, Shilpa. And that if you provide the activation energy, will it continue on its own? Compare that with a cup of water, right? If I take the match and start heating the water, is it going to boil if I take the match away? No, it will not continue on its own. It's not a spontaneous process, not a reaction, process to become a vapor. All right? That's kind of the deal. All right? Will it continue on its own or not? Good comment. Good. Any other questions? Type them in. Let me know. So let's now talk about some reactions. I think I like what Cheryl's done here. I'm on page 450. So I'm going to just like copy her, okay? So I can talk to you about it. So let's talk about delta H and the delta S and the delta G. And here's a reaction. Let's have 2 ozones going to 3, 2 O2 going to 3. Oh, God darn it. Oh, no, it's 2 O3. 2 ozones, O3 going to 3 O2s. And they're both gases. But look, on the product side, I have more gas. So the delta S is positive, right? Because I got more gas I'm forming. I got 1 more mole there than I do here. All right, the delta H, it turns out, and there's no way for you to know this really, it gives off heat when I go this way, so it's exothermic. And so the delta G, if you think about it, let's put that down off to the side. Delta G equals delta H minus T delta S. Well, if the S is positive, then if I put that in, then I still got this negative sign in front. So that's going to make this whole term negative. And look at this. If the delta H is negative, then I got a negative plus another negative. Negative, that's always going to be, so we're going to have negative always. You know what I'm saying? Because if I got one term is negative and the other's negative, then delta G is always going to be negative. Well, what if I do the opposite? So I'm going to do 3O2 gas forms 2O3 gas. Well, for this one, obviously I'm making less moles, so it's going to be a negative delta S. And turns out if I turn it around like that, it's going to be positive here. And so if I got a negative delta S, that negative times a negative is a positive, and I got a positive here, then this sucker is going to be always positive. And that's a good example. So to make ozone under most conditions is difficult because it's got a positive delta G. You talk about the ozone hole. Yeah, well, it's because it's hard to replace that ozone up even at those conditions up high. Okay? It doesn't happen very spontaneously under most conditions. Now you know why the universe cares. It's important if delta G is negative or positive. Negative, we get plenty. Positive, it doesn't really happen much. That's fine. That's fine. Go ahead, Rhea. Just thank you, Rhea. So just watch the rest of it on video. We're going to go a few more minutes, folks. I know I didn't take a break or anything, so let's go maybe like till 25 after, okay? We'll finish up this topic at least here. Good. Let's do then one like this. Let's do the one I gave you a moment ago. You ready? So we're going to do CaO, solid, plus CO2 gas. It's the opposite of the one I gave you a couple minutes ago. Makes limestone, CaCO3 rock solid, rock solid. And you can tell it's getting less spontaneous, isn't it? Because it's getting, well, back up. It's getting more ordered. So the disorder is going to be negative here. It's getting to be a solid. Remember, more disorder is positive. Here I have less disorder because two particles are becoming one, and I lose a gas on this side. It just becomes a solid, so it's more ordered. So negative amount of disorder. Okay, and as it turns out, if you run the numbers, this is also a negative here. So here's the scoop ski. Now I got two negatives. What does that mean? Well, that means that if the temperature is really low, then the delta H runs the show. And the delta H being negative makes delta G negative. So we're going to say negative delta G at low T. But we're going to have a positive at high temperature. Think about that. If I put in a big number here, then this term gets bigger and bigger and bigger. And that's a negative times a negative, so I get a positive delta G if this becomes really big enough. And that makes the total delta G also positive or non-spontaneous. So it's spontaneous at low temperatures, okay? By the way, this forms easily in the ocean. That's how we get limestone. That's how critters can make their little shells out of limestone, right? Shellfish and snails and stuff, calcium carbonate. So low temperatures, that's very possible. It's a negative delta G. It's spontaneous. They can do it. But at high temperatures, this stuff breaks down, so it's not spontaneous. And let's just reverse that sucker and think about it. So again, here's my limestone. And if I break it up, so now we're talking decomposition. into calcium oxide called lime, and that's a solid, plus CO2 gas that's given off. So clearly that's getting more disordered. So I'll put a plus here. And if I run the numbers, I got to put in energy to do it. So it's going to be a positive here. In other words, it's endothermic to break that stuff up. So to break up a chunk of limestone, I got to put in a lot of heat. So what that means is it's not very spontaneous, not at a low temperature. So we're going to have a positive delta G at low temperature. Now think about what that means. I know I'm throwing a lot at you. Positive means it's not going to happen. And it's not going to happen because if I have the temperature low, then there's very little minus portion of it. And if the delta H is positive, which it is, because I'm breaking something up, I got to put heat in, it's endothermic, then the positive rules the day. And the negative portion is very small. So it's going to be not spontaneous at a low temperature. But if I heat up the limestone, heat, then the T gets really big and the negative portion becomes bigger. So it gets more spontaneous at a high temperature. That's what companies do. They heat up limestone to get lime, CaO. And it's spontaneous, but I got to turn the temperature way up. Okay? On the AP, there will be lots of questions. Thank you, Aaron. I understand all you have to go. It's okay. You guys go and get to class on time. I'll finish up blathering here in just a couple more minutes, and then I'm going to stop. Okay? At any rate, this idea is going to be asked about on multiple choice questions on the AP, at least there. Why? Because there are quick ways they can get the student to realize, to see if the student understands this equation. Okay, does the student understand that at high temperatures, this portion becomes more important? Or at low temperatures, it's very unimportant. Okay, and then the delta H is then more important if T is low. So that working with this equation and these ideas in this chart is really what you've got to be able to do with confidence. Okay? I'm going to mark the page in my book, and we're going to do more of this tomorrow. And I know that a lot of you cannot be there tomorrow, so I would just call it a video tomorrow. All right? Thanks for showing up. Thanks for participating. Have a good day. I'll record this and put it in the stream. Bye-bye. Bye, Leah.